Now to run our RNG model, go to Apache. Always save, of course. You can double check the project location in the bottom right here, and from the bottom left, click on Apache Sim. Make sure that MacroFlow link is selected, as well as the last 3 links. You can see the simulation is run for the entire year. You can change the months if you know your peak conditions, otherwise just leave it run for the entire year. Generally won't matter because the Apache Sim simulation usually doesn't take up that much time. Now go to Output Options, make sure all of the spaces and rooms are highlighted, and select all the output options here. Click on OK, and then Simulate. Go ahead and close the window, and let's go to Vista Pro, where we could view the simulation results. Click on your space and the graph tab over here. Now we can see our air temperature in the space throughout the year, and you could monitor a lot of the readings from the energy simulation. You could see that the curve here flattens out because we have a continuous set point. This reading is particularly important because when we run the CFD simulation, do we want to run it during occupied hours or non-occupied hours? In other words, what's the specific operating condition that we're running the CFD at? Is our air conditioning system on, off, or running at partial load? Currently we have it on. If we want to turn it off, we can close this window, go back to Apache, go to the tabular space data, and turn the set points off. Now we have to rerun the simulation. So let's go ahead and do that. Go back to Vista Pro, and now we could see our air temperature has a wider range because the set point is off and the air conditioning is off in the space. Now, if we want to see where our peak temperatures are, we can either click on the peak points, or in the calendar in the bottom right here, we can click on the month and it will narrow it down to the days. And here we can click on the lowest point and see when our lowest temperature is red. So now we have January 5th. We can go ahead and close that. And now we need to export the results. So we'll go to the Vista Pro tab at the top and then export boundary condition. And we know when our lowest temperature, so we could select it and click on OK. Go back to MacroFlow CFD. Go back to our space and then import the boundary data that we've just exported. So click on the boundary condition. This is the file that we just generated. And then here we can override our window and door opening areas, and we can override the infiltration or exfiltration. Let's go ahead and click OK. And now if we go back to the components view, now the room heat gains should be picking up the Apache loads. You can see it here on the left. And on the right here is the MacroFlow CFD components loads. So the 2 people and the radiator. Now, you don't need to have both, but the heat generated from the radiators and the people is the one that's going to appear in your CFD results. If we want to look at our geometry render, we can click on the model viewer up here. And we could see a render of the room that we've created. You could play around with the view settings. And this is quite useful when you're presenting your CFD report. And lastly, before we run the CFD simulation, I want to go over the grid settings. Now, here we can adjust the size of our mesh, and we got to be very careful with how we set up our mesh. If we make it too small, you could see here, if I make it really, really small, IES won't even allow me. If I do it at 0.01, which is still very small, but you could see here IES has accepted it. If I generate my grid here, you can see my mesh is very fine, and my ratio is 2:1. Theoretically, the finer the mesh, the more accurate the simulation is. But there is a point of diminishing returns, as the finer the mesh is, the longer the simulation will take to run, and you might not notice a difference in accuracy. Conversely, if the mesh is too coarse, let's say I make the grid at 0.1 meter and generate the mesh, you can see that the aspect ratio is above the recommended 10:1, meaning that your simulation might not converge or reach a steady state to provide reliable results. If I go even further, IES will reject the aspect ratio altogether and won't allow me to run the simulation. In my experience, I find that 0.05 to 0.04 is the sweet spot for the cell aspect ratio. But you can experiment and fine-tune your mesh for better results. So lastly, in the CFD grid statistics, the green ticks are an indication that our hardware is capable of running the simulation. So now, let's click on OK. And this brings us to the CFD monitor tool. Now, you don't really need to understand the numbers that you see in front of you, but very, very roughly on the top right, you have your CFD methodology. The KE is the default. It's the most generally accepted and widely used turbulence model. It calculates turbulent viscosity for each grid cell, solving for two equations, one for turbulence kinetic energy and the other for the rate of dissipation. The second model is the constant effective viscosity. It does not attempt to calculate turbulence and only does laminar. So it makes for a more approximate and faster simulation. Usually this is used to test out a model to validate it before running a more intensive KE model, but we could ignore it for now. The number of iterations is basically how many times it runs. The simulation needs multiple iterations as the equations have a degree of difference or residual, and they need to run multiple times so they could converge and produce more accurate results. Essentially, more iterations means a longer simulation and more accurate results. The actual number of iterations really does depend on the size of the model. If it's a fairly simple room, like what we have here, I generally find 150 to 200 iterations to be adequate. If it's a large space, like a lobby or a galleria, then you might need 1500 or 2000 iterations to have your simulation converge. Now, for our case, let's just do 100 iterations and click on Run. And you can see it's converging almost immediately, and the iterations are running fairly quickly. Again, this is because our model is very simple. If on the other hand you are running a simulation for a large lobby, you have many components, you're running it at 2000 iterations, that simulation might take you a day or two to begin converging. So it really does depend on the size of your model. Here's an example of a project where the simulation started converging only after 1000 iterations. And here, it took 1500. Now that we've successfully run our simulation, we could begin looking at the results in the next section.